And of course, the reactions would be single phase. So this was at t equals 0, which corresponds to about August 29th or so. All right, so we start out talking about all these assumptions. And in the last chapter, we got rid of, well, the first thing we got rid of was single reactors. We got rid of this assumption when we went to multiple reactors in series and parallel. And recycle. So we spent the whole chapter going through that. The next thing we did is we got rid of this assumption where we went to selectivity. The next assumption we're going to get rid of is isothermal reactions. Now, and what you can see in the coming attractions, sort of like on TV when you watch one of these series, they always at the end of the class, at the end of the show, they show you a couple of scenes of the next class, so you'll be anxious to come back. In future classes, we're going to get rid of these assumptions. So I know you can't wait. But in the meantime, we're going to start getting rid of the assumption of isothermal, because in real life, none of these assumptions often hold. But the approach that we take in this class, and generally, is, and this is sort of an approach in science in general, when you have a hard problem, you don't immediately try to tackle the hardest possible variation of your problem. What you try to do is you try to simplify, 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 simplify. And you get it down to a problem that's one that you can understand and that you can try to solve. Hopefully you don't simplify it so much that there's nothing left, that it's totally trivial. You simplify, as I think Einstein once famously said, that a scientific model should be as simple as possible, but no simpler. So you start with the model that's as simple as possible, but no simpler. Then what you do is, once you understand that, you put back one complication that you had taken out before. And you see if you can still understand that using the intuition you gained from the simpler problem. And that's the approach we're taking in this class. We took away as many complications as we could. We got to a point where we thought we understood what was going on, and now we're putting back one complication at a time and seeing if we can understand it. So that's the approach. And now we're up to the point of taking out the isothermal reaction. Okay, so let's notice what exactly could be happening when I take out the temperature. If I take out the assumption of isothermal reaction, that means things don't have to be the same temperature in all places and at all times. So let's think what that means. So one thing that means is, of course, certainly I can choose a temperature, but I can choose many temperatures. So let's say I have a plug flow reactor. In a plug flow reactor, what does that mean? What can I choose the temperature as a function of? Z. So in this case, T might be a function of Z. That's something I can choose now. Now this is a function that I can choose, or you can choose. And I have a lot of choices, because there are a lot of Z's. There are an infinite number of Z's. So it's a function that I choose. There's a big whole space of functions I can choose. How about if I look at CSTRs? Well, actually, before that, let's look at batch reactor. In a batch reactor, what can I choose T a function of here? Time. Good. So T can be a function of time. Well, let's go to the CSTR. If I have a CSTR, can I vary, what can I vary T with here? Is there anything obvious to vary T with?
Conversion of the object.
I'm listening.
Conversion of the
Conversion. Well, the T affects the conversion. So I want something that, remember, this I can manipulate independently. I can choose t as a function of z. And there are all the z's are in the system. I can here choose t as a function of time, because I choose that. I can't do t as a function of xa because there's only one xa here at the outlet. So I don't have a bunch of xa's to choose different t's for.
Flow rate.
Well, again, flow rate is in tau. Once I have a tau, I'm stuck. There's only one flow rate.
Can we use time?
It could be time.
Well, if I had an unsteady reactor, it could be time. But for a steady state reactor, I really don't have anything to play with. So rather than talking about a single CSTR, I talk about n CSTRs in series. And then what can I vary t with? J, yeah, n. T is a function of j, where j goes from 1 to n. So usually when I talk about a temperature profile, and in particular I often talk about an optimal temperature profile. Presumably the whole point of the analysis is to come up with a good a temperature profile that gives me a better result than any other temperature profile, or at least a pretty good one. So we call it an optimal temperature profile. In a batch reactor, it's T of T. In a plug, it's T of Z. In NCSTRs in series, it's T of N. So that's what I mean by a temperature profile, or an optimal temperature profile. Now, if I have, what are my goals here? Now, again, when I look at non-isothermal reactions, I want to go back and simplify first. Non-isothermal, first let's look at single reactions. And then single reaction, single reaction. And when we understand single reactions non-isothermal, then we'll do multiple reactions non-isothermal. So what are the questions? What are the goals? If I have a single reaction, if single reaction only, then my goal is to either maximize XA or minimize tau. The same goals we had before. We either want to get the highest purity product, the highest amount of product, or we'd like to get particular specs at the minimum tau. So smallest reactor, largest molar flow rate. However, once I have non-isothermal reactors, and even with isothermal reactors, but it turns out to be more of a problem in non-isothermal reactors, we have to worry about reactor stability. Again, this can be a problem even with non-isothermal reactors, with isothermal reactors, but with non-isothermal reactors, it's a very big problem. Is that in our analysis of CSTRs and plug flow reactors, we always assume the reactors are at steady state. And we always assume that the steady state is unique. That is, when I write the steady state equations, there's only one solution, only one CA that solves those equations. However, what happens frequently in non-isothermal systems is that, and sometimes in isothermal systems, is you get more than one possible steady state. You may even get certain situations where, and so you get more than one steady state. How do you know which steady state your reactor will end up at? If there's more than one choice, it's not necessarily the case that the one that's 98% conversion is the one that the reactor will operate at. It may operate at the one that's only 5% conversion. So there are issues of stability. How do you get it to go to the steady state you want, and how do you get it to stay there? And you want to make sure that the steady state you're looking for is stable. You want to make sure that small perturbations don't drive it away from that steady state. So what that means is, a lot of times just doing a steady state analysis isn't good enough. You have to understand a little bit about the unsteady case as well, because your reactor might not be steady. You think you want it to be steady, but it may not be. So we'll discuss that in the context of this topic, but not right away. So before I go through that, I would like to talk a little bit about basic reaction thermodynamics. Because that's a little bit of the background here. Thermodynamics of reaction. And our basic idea is to get a little bit of an understanding about the heat of reaction, and also about what the equilibrium constant is. So the goal here of this review is the heat of reaction, to see what that is, and also to look at the equilibrium constant and see what it's a function of. And the equilibrium constant is, so this is assuming I have a reversible reaction. The equilibrium constant is something very different from kinetics, complementary. So kinetics, you're talking about when things are changing, and you're talking about how quickly they change. Equilibrium, on the other hand, is when things stop changing. So in this class, we've been talking a lot about kinetics, but eventually when things stop changing, they reach equilibrium. And sometimes the equilibrium gives you a limit on what you can do in your reactor. So if you have a certain equilibrium concentration of reactants and products, but you want more product than equilibrium allows you, too bad. Then you're going to need a separator. But if you let your system come to equilibrium, it's not going to give you more product than the equilibrium allows. So this will give us constrain what we can do. Equilibrium constrains what we can do. And that's why I want you to understand K-equilibrium. And K-equilibrium ends up telling me something about XA max, the maximum XA I can come up with. And I'd like to understand what that's a function of, what thermodynamic variable. Okay, now, has everyone in this class had Thermo 2? So you already finished Thermo 2, or are you taking it now? So in Thermo 2, who taught you Thermo 2? Professor Steinberg. Okay, now part of the syllabus of that class is to do the thermodynamics of chemical reactions. Did he cover that material? Very briefly. Okay, that's better than most classes tell me, no matter what, they say no. No matter what I ask, did he cover? No. The ideal gas law? No. So at least you remember that the topic exists. Okay, so what's the outline of what we're going to do? What we're going to do is we're going to start with the second law of thermodynamics. I'm writing this because there's a fair amount of algebra, and I want you to know where the algebra is going. So we're going to start with the second law of thermo. And from that, we're going to get an expression, eventually, to the equilibrium constant. Well, actually, we're going to start from the let me say it this way. We're going to start from a little statistical mechanics, sort of results of statistical mechanics, which is going to give me an expression for the entropy via the second law. And then from the entropy, we're going to start out with the entropy of a single component in terms of statistical mechanics. And then we're going to calculate the entropy of a mixture. So, single component. And then we're going to get entropy of a mixture. And once we have the entropy of a mixture, we're going to come up with an expression for the chemical potential, mu, of each species in the mixture. And once we have an expression for the chemical potential, we're going to come up with an expression for the change in Gibbs free energy with reaction. And once I have an expression for the change in Gibbs free energy with reaction, I'm going to use that to define the equilibrium constant. And we'll see that what the equilibrium constant is a function of. So that's the outline. There's a fair amount of algebra, but I'll leave that outline on the board so that wherever we get, you'll know where we're going. Are there any questions on what we're trying to do here? Okay, now in the sparse coverage that Professor Steinberg did, how much of this did he do? That's a rhetorical question. Okay, so we're going to do this for the case of a single reaction. Single stoichiometric reaction. So here I'm just talking about equilibrium, so I'm not talking about kinetics. I'm not talking about kinetics right now, I'm talking about equilibrium. So I've got alpha 1, A1 plus alpha 2, A2 plus dot 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 goes to beta 1, A1 plus beta 2, A2 plus dot dot dot. So there's only one reaction, one set of stoichiometry going on here. And so let's start with the second law of thermodynamics. The second law says, or one form of the second law, says that there is a function called the entropy. And ds is equal to dq over t. So second law is I have ds is equal to dq over t. Where S is the entropy and Q is the heat that goes into or out of the system, and T is the temperature. Okay, so now how do I get dq? So this is the second law. So by the first law, dq is equal to dE plus PDV, dE and dW. So that's the first law. I don't need, and E is a state function, so I don't need to borrow through it. Maybe you call it U? What do you call the internal energy? U. Okay, you call it U, I'll call it U.
The question though is, we divided by T also? Because,
T, I'm just carrying it along from here. I only redid the numerator. I left the denominator alone. Okay. So, and U is related to CV. Because, so U I could write as n CV hat dt, where this is the CV per mole. So I multiply n, so the n CV hat is the total CV, CV dt. Over T, plus PDV over T. And I'm going to assume here, I'm also going to assume ideal gases, and I'm also going to assume ideal mixtures. So ideal gases, I have the ideal gas law, and ideal mixtures, I'm assuming there's no excess heat of mixing. I'm going to assume there's no excess heat of mixing, and no excess volume of mixing, no volume excess. Okay, so therefore, P over T, since it's ideal gases, I have P over T is NR P over V. So for P over T, I have NR dV over V. And now what I'd like to do is I'd like to do a process where I'm going to subject the system to a process where I first go from T0 to T at constant V. And then I go from V0 to V at constant T. So when I go from T0 to T at constant V, this term, nothing happens because dV is 0. And when I go from V0 to V at constant T, this term does nothing because it's dt, because dt is 0. So at the end of that process, I do this integral, and I have S, and I'm looking at, so I have S is equal to S0, the amount I started with, plus n CV hat, the integral dt over t. Well, the problem is CV hat is a function of t. CV hat depends on t. Plus nr log v over v0. Then when I integrate ds, I get s minus s0. Okay, now, let's say I, now instead of all of the moles, instead of n0 moles, I only want a certain fraction of n0 moles. So this is, of course, all the moles are of one species. And they're at the reference state. And it's the reference state number of moles. So let's say now instead of the reference state number of moles, I take a different number of moles. So now I'm going to let n differ from n0. But that's not too bad. If n differs from n0, then because this is an ideal mixture, instead of having s0, I have n over n0 s0. So now I have S is n over n0 s0. That is, I don't have s0 would correspond to n0 moles. Now I have fewer moles. And now I have n, and now instead of this being n0, it's n. I mean, here I didn't write the zeros in. So I should have actually written the n0s in. So now I have plus n integral from t0 to t, cv hat, t prime, dt prime, dt prime. But now, instead of having instead of starting out with v0 moles, remember, because I went from v0 to v, now instead of starting out from v0, I start out with n0 over n v0 moles. And I go to v. So now I have nr log. And now instead of, I've got v, but instead of v0, I've got n0 v0 over n. And let's just make sure I got the zeros in the right places. No, of course I have them in the wrong places. nr log. Let's just make sure I got that right. No, actually, I go from v0 to n0 over v0 v moles.
Then the dimension is n0.
Yes, so that's not right. So it's probably v0 over n0. V, let's see, v, and I need an n over n0. So I need n0 over n. So n over n0. Okay, yeah, I think that's right. So now I go from n over n0, v0. So I don't, instead of starting out with v0, I start out with a smaller number. Yeah, I started with n over n0, v0. Then I go to v. That's correct. Thank you. So then I have, and one of these should be v. Yeah. So I have the log of v over n v0 times an n0. So the ratio of this to this is exactly the same. Now I need to to make a few notes here. So notes. Before I continue. Okay, I'm trying to do this didactically so you see where all the steps are. It's easy to sweep stuff under the rug in thermodynamics. So the first thing is that I claim that I'm going to call this thing, this integral, the function of the internal energy per mole. And that's, of course, clear because CV is the amount the internal energy per mole changes with temperature. So when I integrate dt, this depends on the internal energy per mole. So the first quantity is, the first note is f of u over n is a function of, depends on the molecular structure. Clearly, the internal energy depends on the molecular structure. And the second note is f of u0 over n0. So where 0 corresponds to the reference state. Is equal to 0. It's defined as 0. It's defined as 0 so that when I'm at the reference state, that is n is equal to n0, when n is n0 and v is v0, then this is the log of 1, which is 0. And when n is equal to n0, I want s to be equal to s0, where s is the entropy of the reference state. So I want everything else to be 0. So therefore, this is automatically 0. So f had better be 0 then. So by definition, f at the reference state is 0. And that's how I define S0. Okay, the next thing is from thermodynamics, from Maxwell's equations. I know that the S du at V and Nj is 1 over 2. So thermo tells me that the S du at constant V and Nj is equal to 1 over 2. So that's well known from thermodynamics. Well known means you look it up in your thermo book. And let's see what that tells me here. Well, if I look at the SDU, there's no U here and there's no U here. So if I take the SDU, then I get, let's do that derivative. Need some space here. I can do it here, I'll erase it here. So I have the SDU at constant V and Nj. That's equal to, these two terms have no U in them, so they're 0. So I have n times f prime. And now the chain rule, I have to take the derivative of u over n with respect to u. What's the derivative of u over n with respect to u? What is that up to? 1 over n. So that's just equal to f prime. So this is equal to f prime. Okay, and finally, the fourth note is NF fourth note even worth writing. Okay, there doesn't seem to be anything useful in the fourth note that we don't know already, so I'm not going to bother with it. I think I've already covered the fourth note. Okay, so now here I'm still single component, just different numbers of moles. Now I'd like to go to X of a mixture. So I'm here. I know this already. Now let's go, we've done this. So now let's go to S of a mixture. All right, so in S of a mixture, I need to, since it's an ideal mixture, then I know that U of the mixture is the sum of the UJs. I sum of all the components. And S of the mixture is the sum of the SJs. That is, there's no additional entropy of mixing other than the sum of the S's, and there's no internal energy. And of course, all these sums have to be done at the same total V and T. So again, in particular, we're calculating U and S as if each component occupied the same total volume and temperature. So I'm not dividing up the volume. Each of the SJs and UJs are for the jth component if the NJ moles of component J occupy the whole volume. Okay, so and in particular, I'm going to take, so T0, V0, same for all J. But U0, S0, and N0 are clearly different. Okay, so that just says I can add things up nicely. So that tells me that S for the mixture is now equal to the ideal mixture is equal to the sum. So now instead of an N0, I have an N0J. Because I have a J for each one. Or an NJ for each one. And actually, I'm going to allow N0 to be the same for all of them also. N is different, but I'm going to let it N0 at the reference state be the same. Okay, so now I just add them up. So that means I put J on all the N's. So I have the sum NJ over N0, S0, J. So because S0 and J0 change, so they need J's. Obviously, anything without a 0 on it needs a J. And the only thing with zeros on it that need J's are the U0 and the S0. Notice, since V0 is the same for all of them, then I don't need a J on V0, because they're all occupying the same volume. Plus N F of U over N. Where now F of U over N is going to have a different definition. So I need to define F of U over N. For a mixture is defined as 1 over N times the sum J equal of all J of Nj integral from T0 to T